Great, thank you. So I'm going to be talking about the Hindley-Milner type system and the value restriction, the type system at the core of ML. So I understand that some of you may have heard of this type system before, but bear with me, I promise I will say something new about it. Not right now, though. Right now I'm going to say some very, very old things about it. So the key idea in ML is, of course, that you don't abstract over polymorphic values. There are no for-alls on the left of function arrows. So that means you can define polymorphic functions, you can use polymorphic functions, but you can't abstract over polymorphic functions. You can't pass polymorphic things to other pieces of code. So this splits the world into monotypes, which I'm writing with tau, which are the types that don't have a for-all in them, and type schemes, which I'm writing with sigma, which are the types that may have a for-all in them. And then the rule for typing lambdas makes sure to use a monotype for the argument. And this is the key simplification that makes type inference work so well in the Hindley-Milner type system. So if you look at the original typing rules, like the Damas and Milner 82 rules for this, you'll see that there are two rules for polymorphism. There's generalization, where you can quantify over a for-all that's not used in the context, and instantiation, where you can get rid of a for-all, filling in a type of your choice. So these rules by themselves don't define an algorithm. You can't write ML purely off that. To get from here to algorithm W, there are two problems that you have to solve. The first one is, during the instantiation rule, what should I choose? Which type tau would be a good tau to replace with the alpha? And the answer to that is, of course, the theory of unification and most general unifiers, and flexible variables, and so on, none of which I'm going to talk about today. The other problem that you have to solve when implementing this type system is, where should I do these two things? When exactly should I be instantiating stuff, and when should I be generalizing stuff? And to help us answer this question, there are two simplifying principles. And these are really, you can kind of squint and see them in the implementation of algorithm W in the original work, but they were, I think, explained in more detail by a later paper by Tofte. So the two simplifying principles that make ML really implementable are, first, pre-next polymorphism. Rather than allowing for-alls deeply nested inside things, we say that the for-all symbol occurs only at the very top of a type. And we can get away with doing this because this doesn't actually lose anything. We don't actually lose any expressivity. There's nothing is lost here because type with a more deeply nested for-all. Again, I'm only talking about deeply nested on the right-hand side of an arrow. We're still obeying the ML rule of not having any for-alls on the left. But a type like the one on the left with a for-all more deeply nested is completely equivalent to one that has the for-all at the top level. So that restricts the shape of types, so you don't have to think so hard about where to place the for-alls. The second important simplifying principle is let polymorphism. So that's the idea that we don't lose anything by delaying all of our generalization to let and doing all of our instantiation at var. So the intuition here is let is the latest possible point that you could generalize, because let is the point where you're about to give a name to something, and that's the point where you might potentially use it twice. Up to there, just before let, there's not really any benefit in generalizing it, because generalizing it allows you to use it in two different ways, and if you're only going to use it once, then that doesn't matter. So you end up with these versions of the rules, which again, if you kind of squint, you can see them in algorithm W. They were published in this form a bit later. And these are a little bit more complicated because they glue together two rules from the original type system. The one on the left is letGen. It's the one that does generalization right before putting a variable in the context and giving it a type. And the one on the right is varInst. It's the one that pulls a polymorphic type out of the context, instantiates all the variables, and then gives you a fully instantiated type. And the reason these are used is, firstly, this now defines an algorithm. It is completely unambiguous where to do your generalization and where to do your instantiation. And secondly, again, nothing is lost. We didn't lose any generality. We didn't lose the ability to type check any particular programs. This is completely equivalent to the original system, but much easier to implement. But of course, a problem arises on the first extension that you do to ML, which is the attempt to add mutable references. And if you add mutable references and you use the standard gen and inst rule, or even these versions for letGen and varInst, then if it is done completely naively, the resulting system is unsound. So Usually this is blamed on something to do with side effects or mutability. But a point I'd like to make here is it's not actually about side effects, it's about sharing. So to demonstrate this, I'm going to give an example of the problem showing up using a feature that has nothing to do with side effects. I'm using local exception definitions from OCaml. So if you type this into OCaml, it will correctly reject your program because this is a bad program. What I'm showing here is a demonstration of a broken compiler because, of course, I develop OCaml. I am a professional producer of broken OCaml compilers. So here is a particular broken one in which I've implemented the naive ML generalization rules. And here we've got a function which locally defines an exception E, which takes a parameter of type A, and then produces two functions. One of them raises the exception E, and the other one catches the exception E. But if we're allowed to generalize the type A using the normal generalization rule, then I can, on the first half, with the first F42, I can raise the exception, passing it an int, catch the exception, assuming it's a string, and then print an int as a string and explode in a predictable way. So what's going on here is this generalization rule. This generalization rule is saying it's safe to generalize if the type variable alpha does not appear in gamma. And what it's really trying to say is it's safe to generalize if all of the uses of this value won't share the alpha. They all get to talk about different alphas. And the assumption in this rule is that all sharing shows up somewhere in gamma. But when you have features like fresh exception types or mutable references, then you have this form of sharing, like the different uses of the same value can share something important that depends on the type, and it doesn't appear anywhere in gamma. So this was annoying, and there was a cottage industry of different approaches to working out how to ban things like this while not restricting the type system too much. And the one that everyone settled on after a while is one of the simplest. It's Wright's value restriction, which says that generalization should only happen on syntactic values. So I slightly prefer the words used in the standard ML definition and also used internally in OCaml for this, which is non-expansive terms, so that they're, rather than just being values, they're things which, when you evaluate them, the store does not get any bigger. You don't allocate any references or make any new types of exceptions. You don't make anything that can refer in a shared way to the type that you're trying to generalize. So that means that the letGen rule gets even more complicated. We now have, as well as the stuff that we saw in letGen, we now have this additional val thing, which is that we can only generalize if v is a syntactic value. And this is just mildly annoying. It's not like the biggest thing in the world. The system is fine. I use it every day. But just constantly, I have to explain to an OCaml programmer why their program didn't work. And even to people who understand what they think of as the type system, but no, there's this extra thing off the side, this definition of a syntactic value. So I'm going to talk about a different approach to this, about rethinking how the values restriction should work, that will end up with a simpler definition. And it will type a few extra programs, but that's not really why I'm interested in this. I'm interested in not having to explain the value restriction ever again. So the really central point is to go back to those two simplifying principles, prenex polymorphism and let polymorphism. So prenex polymorphism, the idea that all of the for-alls may as well be at the top of the type and we don't lose anything, and let polymorphism, the idea that all of the instantiation may as well happen at vars and all of the generalization may as well happen at lets and we don't lose anything there either. The proofs that those were okay things to do, those were all about the pure ML calculus. Those were before we added references. But what if we have references there from the beginning? What if we have mutable state and exception things and so on? It turns out both of those principles are just false. For instance, with prenex polymorphism, if we have references, those two are just different types. The type on the left is a perfectly well-behaved function. That's a function which, when you call it, it gives you back a reference containing, say, an empty list that can hold alphas. And every time you call it, it gives you back a different reference. So every time you call it, it can give you back a list capable of holding a different type. So it really is for all alpha. The thing on the right says that you call it once, and it gives you back a polymorphic reference that can hold any sort of list. And that's completely unsound if such a thing were to exist, because I could get back this one reference, put in a list of ints, pull it out, and expect it to be a list of strings. So the idea that we can hoist all of the for alls up to top level is simply false when we have mutable references. We really do want to distinguish these two types. The second one, the let polymorphism, it is also false that we can just do instantiation of variables and just do generalizations at lets once we have mutable references. Here is an example of like a perfectly well-behaved program, which OCaml currently refuses to type check. It says, it defines a reference. It defines a function which takes an x of an unknown type. It also allocates a reference. The reference is an int reference. Its type does not depend on the type variable being generalized at all. So if we were able to use the really old school separate gen rule, we could generalize the function as soon as we see the lambda, and it says, well, it takes an alpha and returns a pair of an alpha and a reference, and then we could bind that with a for all type. But using the let gen val rule, the one that MLs actually implement, this thing does not type check, or at least type checks with only a weakly polymorphic type, because that ref shows up before you're allowed to use generalization. So this idea that gen can safely be delayed is just simply untrue. So what I'd like to talk about is a different approach to type checking ML or ML-like languages, where we move away from this idea that instantiation must be done as early as possible and generalization must be done as late as possible, because I don't think that's the right approach for a language that has side effects and references and exceptions and so on. So we're going to move to full rank 1 types. So what that means is we're going to allow for alls, again, still ML, still no for alls on the left of arrows, but for alls can appear on the right of arrows or inside tuples or in covariance positions generally. So these are the original rules for ML for the subsumption relations. So this is this type more polymorphic than that type? So for monotypes, well, T is the same as T, but the two things that we're allowed to do are we can instantiate for alls on the left. So if there's a for all is more general than any of its instances, and we can take apart for alls on the right as long as the variable is fresh. So that's a rigid Skolem variable being used on the right-hand side. To get from there to rank 1, we have to add 2 more rules that say we're just allowed to walk down the right-hand side of functions and into tuples. So that means that for alls are, like, we can do instantiation and rigid Skolem comparisons inside the right-hand side of functions or in the other side of tuples. So this is not particularly new. This is actually, this part of what I'm describing is actually implemented in the SML sharp implementation of ML. So as an example of what that actually means, let's look at these 2 types. So they both describe a curried function of 2 arguments, taking an alpha and a beta and returning a beta, but they differ in the placement of the for alls. Now, the old school way of doing this, of interpreting these 2 types, is all of the for alls are implicitly hosted. And this is, for instance, what Haskell used to do before GHC9, a feature that was removed known as deep subsumption. You could say that these are unrelated types, that these don't unify, these are different. And this is actually what Haskell does at the moment for, I think, technical reasons to do with the quick look in predicativity system that they now have. But the approach I'd like to describe here, the one that's true rank 1 subsumption, is when they're related but not equal. Q is, in fact, a more general type. And the reason for this is Q actually offers more power to its users. Both of them allow the user to choose alpha and beta, but the type Q allows beta to be chosen later. A user of P must commit to a particular beta before applying the first argument, but a user of Q can choose beta after the function has returned. And this is the key idea. This is really relevant to whether this is sound in the presence of references and so on, because what if Q allocates a new reference before it returns its value? So this makes our problem of deciding when to do things, the original problem of where to put generalization and instantiation, a little bit more complicated. So we have now this general subsumption rule. We can, at any time, make a type a little bit less polymorphic by filling in some of its for alls. And the rule that we used to have, the var inst rule of doing all of it as soon as we can, is no longer the most general thing to do. And what we end up needing to do is, instead of doing it eagerly, we do it lazily. We instantiate the for-alls only when we really need to. So only when we're trying to call a function and there's a for-all in the way of the arrow, or we're trying to access a field of a tuple and there's a for-all in the way, only then do we actually instantiate the for-all. So it does mean that we actually get slightly more straightforward typings of very simple rebinding definitions like let f equals g there. So in a normal implementation of ML, let f equals g is type checked with let inst or var inst and let gen. It fully instantiates the type of g, then gets to the let definition of f, then regeneralizes it all. But if we're doing this lazily, then when we see g, we just leave it with a for-all in there, and when we see the let, we just put the for-all back into the context. This is actually, so again, doing this style of instantiation as lazily as possible is also not a particularly new idea. It showed up in a fairly well-read paper by Neil Krishnaswamy and Janet Dunfield of complete and easy polymorphism, where I'm told by the authors they didn't realize they were doing something new because they had assumed this was the standard way of doing instantiation. Just this, do it as needed, rather than doing it all in a big bang as soon as you see a variable. But the bit that's more interesting, the bit that is really the key idea of this talk, is the other end. What happens about generalization? So the standard ML with the value restriction is to instantiate as eagerly as possible and delay generalization as late as possible until let. And we've seen now that we want to instantiate alpha we want to instantiate alpha lazily rather than eagerly, and correspondingly we end up having to make changes to generalization as well. So the original generalization rule with the value restriction looks like this. It says we can generalize something with the normal rules for the variables must not appear in the context, only when it is a syntactic value. So a syntactic value is something like a lambda expression or a tuple construction where all of the components are themselves values. So let's just split that into cases. Let's consider the different sorts of things that we might be generalizing independently. So for lambda abstractions, well, a lambda abstraction is a value regardless of what's in the lambda. So there's no particular complicated side condition there. We can just generalize lambdas. For gen pair, then that requires its subterms to be values. But since we're no longer delaying generalization until the very end, since we're allowed to do generalization wherever we want, and the parts of v1 and v2 in that tuple are in fact already values, then they will already have been generalized before we get to this rule. There will already be for-alls in the types of the components of that tuple. So this rule isn't actually getting us anything. This rule allows us to put a for-all outside the tuple, but because we've got rank 1 subsumption, that's actually less general than putting it inside. So our type system loses nothing by just completely deleting that rule, and in fact, every other rule for generalizing values other than lambda. So what we actually end up with is generalization is a thing that happens to functions. So the type system is you instantiate for-alls when you're absolutely forced to, when you're trying to use something that's got a for-all in the way, and you generalize when you see a lambda. So for I'll give a couple examples of what this ends up looking like. So here, a very standard ML function. We get the same type as we would in ML. We get it for a slightly different reason. The generalization happens because I see a fun rather than it being ungeneralized until I see the lash, but it gets the same answer. Here, we don't generalize, so that's ref of tau rather than for all alpha. That's a variable that we have not generalized yet. And at this point, I would now normally have to do a big digression about the nature of syntactic values. But in this system, I say, no, it doesn't generalize. There's no fun. There's no lambda there. Lambdas are the thing that make polymorphism. Here's the example from earlier that OCaml fails to type check, or fails to give a sufficiently polymorphic type to. And this one is type checked with the most general type because the for all appears where the fun is. The lambda is the thing that makes for-alls. Here's a more complicated thing, which makes an identity function, packages it up with a reference, then pulls it out again. This thing also gets the most general type, because again, the for-all appears where the fun is. Lambda is what makes for-alls. So this is a pair of a for-all alpha, alpha to alpha, and a reference. And we throw away the reference, and we are left with a for all alpha, alpha to alpha. So, I mean, these are not especially compelling examples. I'm not saying that this is a better way of doing it because we get to type check these two functions. They're not things that people normally write. But I just really like to have a type system like this so that I would never, ever have to explain what the value restriction is. So in general, if we switched to full rank 1 types for ML-style languages and dropped the assumptions of prenex polymorphism and the assumption of let polymorphism, then the type system says we generalize all lambdas rather than some lets. We don't need the syntactic value judgments, and yes, we can type a few more programs, but not especially interesting ones. Thank you.
Thanks for the nice talk. Can you go back to the previous slide? Yeah. So here you're saying that you allow nesting the for inside the pair component type.
Yep.
Right. So do you have some? Do you have a subsumption for pairs? Like you have subtyping rules for pairs and stuff like that? Yeah. Right. Okay, but so this works because the pair is covariant, right? So
yes.
what happens if you don't know that? Like, so you need covariance annotations on your data types now, right?
Yes.
If it's
yeah, because the point of rank 1 is that for alls can appear under covariant positions. It's still ML, so no for alls left of an arrow. So yeah, you really do need to know that it's covariant for this to
right,
work.
but you know, Camel, sometimes you don't know if an abstract type is covariant or not, for example, right?
Oh yeah, that's true, and you would not get for alls under
in this
ones
case. So in this case, what happens? You'll have to instantiate the for all, and then you have to explain that to students, right, or to programmers. So you don't explain the value restriction, but you have to explain covariance and the fact that sometimes the lambdas get instantiated for some reason, right?
Yeah, I'm mostly happier explaining variance than explaining the value restriction. Your mileage may vary.
That's good. I agree. Yeah, so it's good to see that you came to the same conclusion. We're already doing this in ML script, right?
Oh, cool.
And I think there were previous systems that generalize lambdas and instantiate at applications, because that's the only way that really makes sense, at least in the call by value semantics, right? You don't need to generalize other things than functions, really.
Yep.
Yeah, okay, thanks.
Hey. So I had a couple of small questions. One was, so the with the arrows here, obviously you can like instantiate in and like not out, like that's assumption, unless you push the for alls in. With the tuples, presumably you could move them in and out a little, like you can go both ways. It's kind of fine because there's no way to like do anything between. Oh, sorry. Presumably with the pairs, putting the for all just inside the pair and the for all just outside the pair.
That's true. I mean, it's not the system I'm describing here, but I agree it would be sound to allow for alls to float in and out of tuples.
Okay. Is there anything that makes it trickier? You just not thought about that, or doesn't really matter?
Yeah.
All right. And the other one was so another thing where you end up needing polymorphism is obviously row polymorphism, kind of like generates another like kind of constructor that like there's you write a if I write something that's just a bunch of polymorphic variant constructors and no lambdas at all, I still need that to come out polymorphic to get the row polymorphism. So what's the rule?
Oh, right. So would you mind if I switch to a simpler example of empty list? Because
yeah,
I think
sure.
it's the same kind of problem, or are rows super interesting here?
Probably the same, yeah, okay.
So yes, so some of these, so there's some types which in ML, for instance, if you have an empty list constructor, the type checker will give that a flexible unification variable and hope for it to be generalized later. But in this style, we're doing generalization as eagerly as possible, so we can't rely on generalization happening sometime later. So it means the typing rules for things which are completely polymorphic have to actually say the for all up front. So the rule for nil is nil has type for all alpha list.
Gotcha. Yeah, that makes sense. Thanks.
Very nice system. I think it's much simpler, much more elegant. But that raises a question in my mind of why haven't we been doing this all along? In terms of like, I would kind of expect historically that something like this would have been developed first rather than let generalization. So what is the fundamental trick that you had to do in order to make this possible that we didn't realize before?
Yeah, so partially I was hoping that someone would say, we've been doing this for 20 years and you haven't found the paper about it, because it's weirding me out that we haven't. I think maybe the thing that's a little bit, I suppose, unusual is there's a non-trivial subsumption relation, so you have to think a little bit about deeply subtyping things. I don't think it's that hard to do, but maybe that might have put people off who came across this before, but yeah, I don't really have an answer to that one. I am wondering about it as well.
On the topic of non-trivial subsumption relations, have you thought about extending it to subtyping? And so instantiation is then just in the subtyping relation, which is not normally the way that, say, languages like Java or C# handle things. They would separate subtyping from instantiation, but does this give you a way to do that, sort of integrate it?
Yes, yeah. I mean, much as Lionel said earlier, I think both of us noticed this sort of thing from doing exactly that in a language as subtyping, and this is me backporting it to ML by deleting all of the stuff about subtyping.
Okay. Hi, thank you for the story. I like the story. Just two independent remarks. In MLF, actually, we do the same thing. We always generalize as soon as possible and only instantiate by need. So the P and Q, we would give a more principal type Q rather than P.
Oh, yes.
The other independent comment is that actually, for example, we can already type in ML. So this is not implemented in Camel, but one of the first prototype I wrote in ML is actually doing not only non-expensive values, but it's doing in the negative way. So you're allowed to generalize everything except what is forbidden to generalize, and then you recover all these examples.
Right, so this is the rule where you can walk down a let binding as long as the thing being bound doesn't mention the...
Yes, so what is forbidden is type variables that would appear in expansive expressions. So everything can be generalized except they appear somewhere unprotected in an expansive expressions, and I think you recover the same example.
Yes. So that's this example here where the ref is because the alpha doesn't appear anywhere to do with refs. Yeah, that works as well. Yeah, thanks.
Okay, thank you for the presentation. First, a small remark here. So you mentioned that it was in SML#, if I remember correctly. Oops. Or recall that rank 1 polymorphism by opposition of rank 0 polymorphism that was the traditional ML style.
Sorry?
Ohri, the author of SML#, called that rank 1 polymorphism. By opposition, he was calling rank 0 polymorphism what you get usually in ML.
Yes, yep.
And the question that you would expect from me, how does it interact with the relaxed value restriction?
Yeah. I have not proven this. Actually, so in many of the cases where the relaxed value restriction allows you to give polymorphic types to things which produce empty lists, or things which produce data types which mention their type variables only covariantly. In many of the examples that the relaxed value restriction type checks, you can get the polymorphism deeply at the point of creation of one of those empty structures, but I don't know whether that covers some of the motivating examples of the relaxed value restriction, but I don't know the relationship between this and the full system, whether it gets the same generality or not.
Okay.
So one of the most annoying cases for the value restriction is when you partially apply a curried function that you know is going to return a closure immediately. So I'm not seeing how this handles that.
So
particularly in the case, I understand it can sometimes handle it, but in the case where, say, the function has the type for all alpha arrow something, and then several other arguments, and you instantiate that first argument.
Oh, I see. Where it really does the first argument really does.
The first argument already has the
yeah. Okay. So in that case, it's not going to help because in that case, you really might be doing the bad thing. That function really might be creating a mutable reference.
Right.
In cases where it doesn't mention it, you can use the type that pushes the for all to the right.
Okay, so you'll still have to explain the value restriction in that case. I mean, basically, that's a case where if you knew that the function was total, then you wouldn't.
Yeah, no, that's true. There's still something to explain there. I think the reason that I like this approach is that I can explain that distinction by pointing at the types and saying the for all is there before the argument rather than there after the argument, but the limitation absolutely still exists.
So currently, when you have something like a reference to a formatting function, I think it's a little bit awkward because you have to do it like the logs module does. You have to define a record with a single field and put your for alls there. Would your system allow an easier way to write those kinds of?
No, it's still so. So the initial ML style assumption of no for alls left of ours means no for alls in positions which aren't covariant. So that includes inside references. So it's still, for things that actually go into references, it's still just as restrictive.
Okay. Hi, could you go back to the examples, because I have some question. And yeah, in the last example with the first function, here you need to instantiate this first function because the first component of the bar is polymorphic. So how you avoid breaking the prenex form here? Because you substitute.
No, sorry. Excellent point. I should be a bit clearer. I'm using a syntax for a primitive projection.
Okay.
Yeah, you have that if you actually, if you lambda expanded, eta expanded first, then that becomes tricky because you are trying to pass a polymorphic thing to a function. Yes.
Yeah, thank you.
Thank you.